Okay, friends, we'll go ahead and get going. So during the break, somebody asked a question that I thought was worth talking about. And the question was, what if you have two different tertiary carbons, A and B? If you have that situation, I do not expect you to predict a regioselectivity preference. So you would get, these two are regioisomers because in the one on the left, hydrogen's on the same carbon as the methyl group, whereas in the one on the right, hydrogen's on the same carbon as the ethyl group. These are carbons A and B. Do you see how these two regioisomers have different connectivity? And we can't predict which would be better because the intermediate, the carbocation, is going to be of similar stability, whether that positive charge is on A, tertiary carbon A, or on tertiary carbon B. And in addition, you would get both the syn and anti-diastereomers and both enantiomers. 4 products here, 4 products there. If you use straight lines, this is shortcut. This one thing is shortcut for all of these. If you draw just the straight lines, you're communicating that we have both configurations at A and both configurations at B for a total of 4 products. 2 pairs of enantiomers that are diastereomers of each other. Okay? All right. Any follow-up question on that? Yeah.
Would that be like a subclass of constitutional isomer?
Yeah, regioisomer is the same thing as constitutional isomer. I suppose you could call it a subclass in the sense that the connectivity is mostly the same, but with a few key differences. Yeah. All right, so your text introduces another reaction as though it's its own thing, but it's not. I've copied and pasted this exact same thing that we did for the hydrohalogenation reaction, and instead we're going to do hydration. So all you do is you change the thing the proton was attached to. If instead we use hydronium, and usually the conditions your text uses for this is H2SO4, but understand that that comes aqueous and it's probably mostly H3O plus and HSO4 minus. In any case, the first step is identical. Pi electrons attack the proton and water leaves. You get a carbocationic intermediate, and here instead of bromide being the nucleophile, water is going to be the nucleophile. The HOMO is still lone pairs on water, and then that attacks from above or below the carbocation, and then you get, everywhere there's a Br here, we can erase the Br and put OH2 plus. We have still the same groupings of products, diastereomers and enantiomers. We don't stop there. Likely, we isolate the neutral alcohol. How do I get that neutral alcohol? What do you think happens? What's that? Yeah, protons, though, don't necessarily leave themselves. They're attacked and carried away. So we can have water remove one of those protons, and that actually regenerates the acid that we started with. So I'm going to copy all of these. I showed you one of those deprotonation reactions, and afterwards we get the neutral alcohol as products. Whoops. Okay, and I realize that if you don't have copy and paste ability on your paper that this is infuriating to you, and I'm sorry. We regenerate H3O plus. So this is actually acid catalyzed, and you don't need a huge amount of acid to make this work. Okay, but you're going to, all the same stereochemical issues apply, the same regioselectivity issues apply. We get the carbocation on the more substituted carbon where it's more stable, and then water, the nucleophile, can add from above or below. Okay, alkene to alcohol. Now, some of you may be thinking, I mean, it's sort of whiplash, but in chapter 9, we converted alcohols to alkenes under acidic conditions, and that's actually just the backwards reactions here. In other words, if you go back to chapter 9 and you start here, protonate the OH group to get the oxonium ion. Oxonium ion leaves to give you carbocation, and then you do an elimination reaction, you could get back to this starting material. Addition of water to alkenes is the exact reverse of alcohol dehydration. Yeah?
What's going on? I don't even know how to describe where it is on the page. Just above the first number 1.
Okay.
Cycle H2O is attacking another H2O.
So water is acting as a base to remove one of these protons on this oxonium ion. So
where did the oxonium ion come from?
That came from the fact that we attacked the carbocation with water. We made a third bond with oxygen. Now that oxygen's bonded to 3 things, so it has to have the positive charge.
Okay.
Yeah. And then this oxonium ion looks kind of like hydronium, only one of the things is a carbon instead of a hydrogen. Its pKa is going to be basically the same as hydronium, so it's very easy for water to remove this proton and for us to isolate the neutral alcohol. Okay. When reactions are in equilibrium like this, you can drive the reaction whichever way you want based on Le Chatelier's principle. For example, alkenes are lower in boiling point than alcohols. So if you want to get the alkene product from the alcohol starting material, you could simply distill off the alkene or remove it from the equilibrium. If you wanted to go all the way to alcohol from the alkene, you might add an excess of water and push the reaction forward that way. There are going to be a few other reactions you learn in 352 that are very similar, where it's acid catalyzed and it's in equilibrium and you can go one way or the other. You'll learn them both ways, and then you'll use Le Chatelier's principle to direct the reaction. So I hope you can see we don't want to think about alkene hydration and alkene hydrohalogenation as separate things. They're identical. The only thing that's different is the nucleophile that attacks the carbocation, but all of the issues are exactly the same. One other thing, I haven't named this regioselectivity phenomenon where we get the bond between carbon and hydrogen and the positive charge at the more substituted carbocation. This is a rule that was originally discovered before people knew a lot about carbocations. It's called the Markovnikov Rule. I don't really care that you know that, but it will come up in your text. And in particular, we're going to find situations that violate this trend, and your text will call them anti-Markovnikov products. But yeah, not a huge fan of memorizing the names of dead people. May they rest in peace. Okay, questions? Okay, so for hydration, as with hydrohalogenation, there's not selectivity for syn versus anti. You get two enantiomer, or pairs of enantiomers that are diastereomers, and the pairs are diastereomers of each other. All right. Oh, sorry, missed you. Go ahead.
Just real quick. So as the hydronium was recreated or regenerated, pH would never change.
That's right. pH doesn't change over the course of the reaction. Yep. Good. Others?
What did you say about sin and anti just now?
That in this reaction, as with the one we did above, you form 2 syn diastereomers, 2 anti-diastereomers. The 2 anti products are enantiomers of each other. The 2 syn products are enantiomers of each other. So we have 4 different diastereomer relationships and 2 different enantiomer relationships among the 4 products. And we don't expect to see any selectivity really for syn versus anti, at least not any that we will predict. Okay, there's a couple more reactions. The next 2 are do show a preference for the anti-diastereomer and none of the syn. And the reason for that is you don't go through a carbocation. So let me show you how this reaction works. This is called alkene bromination or halogenation. And we're going to take an alkene, and I'm using cyclohexene just as a convenient alkene where we can see these stereochemical relationships. We're going to add Br2 or Cl2. The product that we're going to get is exclusively the anti-diastereomers, and we'll get both of these enantiomers because, as before, whether we attack from above or below doesn't matter if we're using an alkene where the HOMO is the pi bond that's evenly distributed on both the top and the bottom face of the double bond. But do you see how these are both anti-products? Because the bromines that we added are opposite each other relative to the original alkene. We don't get anywhere, the BRs are on the same side. And the conclusion is, the question is, why do we just get anti? And the answer is, there is no carbocationic intermediate. Okay, so first, let's deal with the fact that both carbons A and B get a bond with Br. One of them will get it first, the other will get it second, but you can't tell because the 2 bromines are identical. So there are essentially no regioselectivity issues to keep track of for this reaction. Yay. So we're not going to worry about who gets what bond first because in the end both of them have a Br. All we have to account for is why they're on opposite sides. So this can be a little tricky. So hang in there and I'll talk you through it. All right, the HOMO of the alkene is the pi electrons. And the LUMO of Br minus is the bromine sigma star. Okay. Now, if we were doing this reaction just like we did hydrohalogenation or hydration, you would expect the pi bond to attack one of the BRs to give you a Br on one side and a carbocation on the other side. That doesn't happen here because unlike the 2 previous reactions where the thing that the alkene was attacking was a hydrogen, the thing that the alkene is attacking here itself has electrons on it, relatively high energy lone pairs. And so at the same time as these pi electrons are attacking the sigma star and breaking the bromine-bromine bond, the lone pairs are going to snap back on the other carbon, the one that doesn't get the new carbon-bromine bond, and close that up into a three-membered ring. Alternatively, the alternative would be to have something like this. And if you made that, bromine is going to actually lean over and make another bond with that carbon A. So we don't see this intermediate. Instead, we form a bond between carbon B and bromine at the same time as we form a bond between bromine and carbon A. And we can't actually tell which of those two bonds comes from the pi electrons and which come from the lone pair on bromine. All we know is that we get this intermediate, which has a positive formal charge on Br. Okay, questions about that? It's a concerted reaction. Yeah. Sorry. Oh, right. Yes, you're going to get the top face and the bottom face of the alkene are going to be identical. I didn't think to draw that because it turns out that this intermediate is not chiral. It's got a plane of symmetry. These two are actually equal to each other. Okay. Now, the intermediate that has a positive charge on bromine is called a bromonium ion, or if it were chloro, it would be chloronium ion. Halonium is the general term. It's kind of like oxonium or ammonium. You have a positive charge on an atom because it's bonded to too many things. Notice that bromine comes with 7 valence electrons. It currently owns 2, 4, 5, and 6. 7 minus 6 is a positive formal charge. Right? So then Br minus can act as the nucleophile. The bromonium ion is not as strained as an epoxide. It has the 3-membered ring, but remember carbon-bromine bonds are longer, so the ring isn't quite as tight and strained. Nevertheless, you got a positive charge on bromine, and so the carbon-bromine bonds are weaker in the bromonium ion, are weaker than a regular carbon-bromine bond would be. And so we're going to have Br minus attack from the backside in SN2 fashion and leaving group leaves. Now here I'm showing you attack at carbon A. I could have just as easily showed you attack at carbon B. I'm only showing you one of those options here, but you would also get, if we attacked at B, you would get the other enantiomer, and of course we could, yeah. So these are our products, and they're enantiomers of each other, but the key is that the bromo groups are anti to each other relative to the original alkene. Go ahead.
So, did you say that this is a concerted reaction, or do we have that intermediate?
I'm sorry. I guess by concerted, I meant forming of these two bonds to the bromine ion is concerted. But we do have an intermediate that gets attacked from the reverse in SN2 fashion. This is like epoxide opening. And yeah, therefore we get the anti-product. Okay, questions about that? Sure, go ahead.
I think there was a place in the guide where I talked about like the second step with the bromine coming in, like if it's different on the top and bottom, on a certain side.
Yeah, the question is, what if I started with an alkene like this, such that after the first step, I got this bromonium ion. And of course, because the alkene can attack from its top face versus its bottom face, I would get, whoa, that's not reasonable. I would get that other intermediate. And then you could ask which carbon, A or B, does bromide attack? The problem is you can't tell, because both carbons get bromine. So if I attacked at A, I would get this product, but I could also get that product if I attack down here from B. So, do you see? Yeah. So, and I guess to be complete, I will just finish. If I attacked at B, we would get this. So, sorry, having a hard time talking and thinking. So it turns out that I really can't tell, because I could explain the products I observe through multiple pathways. Now, there's evidence to suggest that the nucleophile does attack the more substituted carbon preferentially. And the evidence for that happens if you do this reaction in a solvent that can also be a nucleophile. So imagine that we take the same starting material, and we're going to use Br2, or, for fun, let's just use Cl2. But we're going to do this in, say, water. And water, as you know, is, if water's our solvent, it's highly concentrated, about 55 molar if you calculate it knowing the density of water. So what's going to happen is, yes, the pi bond will attack the chlorine. At the same time, the chlorine attacks the other carbon, and we're going to get the halonium ion, in this case chloronium ion intermediate, and Cl- was our leaving group. But at this point, Cl- disappears into the solvent, and your molecule is surrounded by way more water than it is Cl-. And so the nucleophile in the second step, rather than be Cl-, is water. So we will have water come in and attack. Again, this is just like epoxide opening in the sense that we're going to attack from the back side. That's going to give us an anti-relationship between chloro and the water nucleophile. A and B in this case are identical, so I would have to get the other enantiomer as well, which I will draw here. And then finally another molecule of water. Your text will often show actually Cl- doing it, but it's way more reasonable to show water removing that proton, because Cl- is a much weaker base than water is. And that will give you this product where we have this 1-2 relationship between hydroxy and chloro, and these two are enantiomers of each other. Okay? Now, that doesn't address the regiochemical question, right? Because I started with something where A and B were the same. But if you have the nucleophile coming in at the second step being different than a halide, then it's possible to tell which bonds form first. But before I do that, so what we're going to do is we're going to repeat this reaction, only we're going to use, instead of Br2, we're going to use some solvent that can be a nucleophile. And then we'll answer the question, which carbon gets attacked in the second step. But questions so far? Okay, what I just showed you, your text calls halohydrin formation. But it's not a, because the product where you have this 1-2 relationship between chloro and hydroxy, that kind of product is called a halohydrin. We get exclusively anti-products. We don't see any of the syn products, and the reason for that is opening of the halogenous ion is an SN2 process. We never have a full carbocation. Yeah?
Why was the chlorine one different than the bromine one?
The only difference here, it has nothing to do with chlorine, and I'm sorry I switched because I probably communicated inadvertently that it has to do with chlorine. If we just use chlorine, we would get the exact same products here. The difference is we're using water as a solvent. Up here, water is not present. Yeah?
Where you just box the SN2 where it's
Yeah.
the agent is a chloride ion?
Well, that wasn't meant to be above the arrow. Chloride is the leaving group that leaves,
Okay.
and water sort of outcompetes
Okay, that was my question.
Cl minus. Yep.
That chloride ion is just
No, I'm not adding the chloride ion. It was the leaving group. Oh, wow, I'm missing an arrow. That makes me feel a little bit better. Okay, what else? Yeah.
Those two products at the bottom, those are both that come up in equal amounts.
Yes, these two products at the bottom are enantiomers of each other. Oops, dang it. I kind of wanted to move it over. There we go. Yes, they are indeed enantiomers of each other. They have to form in equal amounts. We don't see any of the syn diastereomer. All right, so let's deal with the regiochemical issue with that sort of pesky example. Let's use the methyl cyclohexene. Let's use Br2. And in this case, maybe just to shake things up a little bit, instead of using water, I'm going to use methanol as my solvent. But it's going to be a solvent where I have high energy non-bonding lone pair electrons that are going to outcompete the nucleophile for attacking the bromonium ion. All right, we're going to focus on regiochemical issues for this step. So pi electrons attack Br, and then Br lone pairs attack the other carbon, and the bromine-bromine bond breaks. And that gives us this halogenous ion, this bromonium ion, which we can draw like this. I'm going to just say plus the other enantiomer because I don't want to draw it. But that other enantiomer we would get if the alkene used its bottom face to attack the Br. You okay with that? Doesn't matter. I'm too lazy to draw it even if you wanted me to. Man, okay. Fine. Fine, I will draw it. Okay. Now, Br minus was our leaving group, but it's going to get outcompeted by methanol because the concentration of methanol when it's the solvent is really high. Which of the two carbons should it attack? And what we're going to do is to consider the analogy of this bromonium ion. It is like a protonated epoxide in the sense that you have a three-membered ring with a really good leaving group as part of that ring. And actually, you would expect the Br plus to be even a way better leaving group than the than the oxonium ion. Okay, so before with the epoxide, we said that the fact that you have a good leaving group in this three-membered ring moves the transition state further down the leaving group leaving pathway. So it involves a buildup of positive charge on the more substituted carbon where it's more stable. We're going to apply the exact same principle here. The bromonium ion has this positively charged bromine, which is a good leaving group. The transition state for this reaction is going to involve lengthening of the bromine carbon bond with the lengthening of the bond between bromine and the more substituted carbon, because that more substituted carbon can better tolerate the buildup of partial positive charge in the transition state. Like we said before, this carbon is somewhere intermediate between tetrahedral and planar. So it's not quite tetrahedral anymore, it's flattening out. And then in the same sort of step, the nucleophile is coming in from behind, though it's doing so to a much lesser extent than the leaving group is leaving. So we got the same situation with the epoxide. See the analogy? Okay, so methanol will attack the more substituted carbon because that one better tolerates the positive charge in the transition state, and the leaving group leaves. So the products that we get are, let's see. Okay, if we attack the molecule on top, we should get this product. If we attack carbon A of the molecule on the bottom, we should get its enantiomer. And then some base, likely more solvent. Your text might show the Br minus ion doing it, and that's fine too, but we're going to remove the product. We're going to remove the proton to get the neutral product. And note the anti-relationship between the nucleophile that came in the second step and the bromine where we formed the bond in the first step. Notice that those groups are anti to each other, and then notice the fact that the nucleophile, which came in the second step, is on the more substituted carbon. So, I mean, this is a long answer to a short question, but by analogy, people speculate, though you can't tell, that back if you were to do this reaction just with bromine, they speculate that bromine in the second step, Br minus, preferentially attacks the more substituted carbon. Of course, you can't tell, but if you bring in the solvent as a nucleophile in the second step, then you can. Okay, questions? Yeah?
What took away the H in the final step?
What took away the H in the final step? More solvent molecules. Yep, so I should have showed maybe MEOH2 plus as a product. We also had Br minus as another one as well. Okay, other questions? Yes?
Why do you get two products instead of just one? I guess what I'm asking is, where does the attack from two?
Okay, why do we get two products instead of one? The two different sides happens here in the first step, where the two faces of the alkene are identical. We could attack bromine from the top face of the alkene or from the bottom face. If we attack from the top, I wanted a pen. If we attack from the top, we get this one. If we attack from the bottom, we get that one. Yeah. So that's where the two enantiomers come from. The reason we only have two products and not the other regioisomer is that the transition state has a buildup of positive charge on the more substituted carbon where it's more stable. All right, other questions? Yeah.
And just at that step, the methoxide is attacking the opposite side of the bromide.
Right. Yep. Yeah. It's still SN2, but it's SN1-like in the sense it's SN1-like in the sense that you have this buildup of positive charge. It's still SN2 because the nucleophile still comes in from behind. Yeah.
Can you point out where the halohydrin?
Yeah. So the halohydrin, I'm not sure what you call it when it's an alcohol that comes in instead of water, but this pattern of a halide and OH on adjacent carbons and they're anti to each other, that's a halohydrin. Yep. Okay, what else? Okay. So that's 4 new reactions in chapter 10 that you've learned. Hydrohalogenation of alkenes, you've learned hydration of alkenes, you've learned bromination or chlorination of alkenes, and you've learned halohydrin formation. But the first two, hydration and hydrohalogenation, are 2 examples of the same principle. Go ahead.
Oh, sorry, this was kind of before. Like, just kind of in general, when you're doing a reaction in a solvent, how do you know, like, which one's going to act as the nucleophile?
Right, if you're doing a reaction in a solvent and the solvent can be a nucleophile, it will almost always outcompete the other things.
Okay, so just assume.
Yeah, so that's why I showed methanol attacking here instead of Br minus.
Okay, but like, why would like the methanol not attack like in the first step?
Attack where?
So like what?
What could happen here? Well, the issue is methanol can't attack the alkene because we're using the alkene as a nucleophile. The pi electrons are high in energy. The pi star would be the LUMO of this molecule, but methanol is not a good enough nucleophile to attack that pi star, which is pretty high in energy. So yeah, the fastest thing to happen is this first reaction, and then methanol comes in the second step. Good question. So those first 2 reactions, hydration and hydrohalogenation, were identical in mechanism. The only thing that was different is what is the nucleophile in the second step. Similarly, halogenation and halohydrin formation are identical in mechanism except for the nucleophile that comes in the second step. With both halogenation and halohydrin formation, we get only the anti-products, but with hydration and hydrohalogenation, we get a mixture of syn and anti-products. So I know this is a lot. You're going to have to practice it, but focus on the commonalities between these mechanisms. See them as different manifestations of the same basic principle. All right, see you Friday.
I have like 2 questions. Sure. The first one